3, the definite integral. Again, it's not really difficult stuff, so you will probably enjoy it. Homework will not be too tedious. It'll go pretty quickly. All right, so let's take a look at it. I have a brand new pad of graph paper. This is my first piece. The definite integral. Okay, so we're going to do a little bit of integration here. But again, if you already have an understanding of integration from high school or wherever, you need to kind of hold off and try not to jump into those skills you already have too early. So we're talking here now again, or we're continuing to talk about the area under a curve. And what we have learned is how to get an estimate of the area under the curve by creating rectangles and taking the area of all the rectangles, summing up the areas of all the rectangles. And we've learned that the smaller the width of the rectangle, the more accurate we will get for the value of the area under the curve. So what we're getting ready to do now in section 5.3, and I'm going to go to the textbook and read. He's done a very good job here of writing a kind of an overview of what's going on. So I'm going to read it on page 268, what Mr. Thomas has to say. It's at the top of this page 268. And it says, we return to the problem we started in this chapter of defining what we mean by the area of a region having a curved boundary. We approximate the area under the graph of a non-negative continuous function using several finite sums of areas of rectangles capturing the region, some being upper sums, some lower sums, and some sums using the midpoints of each interval. So that was kind of that long, tedious homework section. All being cases of Riemann sums constructed in special ways. Now, Riemann, remember, his method of finding the sum does not restrict the width of the rectangles to being one value. He will let the width of the rectangle be random underneath the curve in order to get more accuracy. So he'll make it really narrow in places where the curve is dramatically increasing or decreasing, and then widen it out where the curve gets a little more constant. Theorem 1 below guarantees that all of these Riemann sums converge to a single definite integral as the norm of the partitions approach 0 and the number of subintervals go to infinity. Okay, so the norm of the partition means that when he varies the width of the rectangles under the curve, making them extremely small, the norm of all of his rectangles is the largest width of all the rectangles he uses. Okay, so the norm is the very largest width he uses of all the rectangles. And then, if all of his rectangles are so extremely narrow in width, then you're going to have infinitely many rectangles. The more narrow each rectangle, the more rectangles you have. And so if you let the width approach a value of 0, then you'll have infinitely many rectangles under the curve. As a result, we can now define that the area under the curve of a non-negative integral function to be the value of the definite integral. So we've already learned a little bit about integration, and now we're saying integration is going to give us exactness in finding the area under the curve. So here it is. If your function is a non-negative and integrable function over a closed interval, then the area under the curve, y equaling f of x, in the interval of a to b, is this. The a, meaning the area under the curve, is to integrate your interval from a to b of f of x dx. So there's your definition that says, yes, we can get the area under the curve through the method of integration. Okay, so here's what we come down to now, and I'll write this down because you really should write this down also. The area under the curve is the integral from a to b of f of x dx. When you're looking at your function, an integrable, that's a hard word, an integrable function, the function is, you can integrate the function, okay, on the interval from a to b. Okay, so if we can figure out how to integrate, then we're good now at finding the area under the curve. Well, the way this is read, this a, which is the lower bound of your interval, is called the lower limit. Okay, it's called the lower limit. And the b, which is the upper bound of your interval, where you're finding your area under the curve, is referred to as the upper limit. Okay, you got an upper and lower limit. Then this is your like elongated s, which is the symbol for integration, is the integral. This function, f of x, is considered the integrand. And, I don't use that word a whole lot, but it is used in the textbook if you're reading along. And when you have dx, this is your variable of integration. In other words, your variable of integration is x. Okay, your variable of integration is the x variable. So you have an upper limit and lower limit. When you integrate this function between a and b, that's how we would write it. Now, something else he talks about when he's talking about the Riemann sum, which is still in this book, and I'm going to back up a couple of pages on page 264. Now, Riemann has some interesting notation. But Riemann says, that doesn't look like the right page. Here it is, page 263. Hold on, that's not quite it. His notation gets pretty hairy. Here it is at the top of page 264. Here's how Riemann makes it work. See if I can hold this still. Right, here it is. We have many choices for the partition with the norm, the width, the largest width of all the tiny little rectangles going to 0. So the width of rectangle going to 0 has many choices of points, C of k, for each partition. So in other words, here's a sum, that summation symbol we've discussed, okay, of this function times delta x. This is like your height of your function times your width. So the sum of the height times width are the sum of the areas of the rectangles. This having your width be so tiny that's approaching 0. So your limit as your width approaches 0 of the sum of your areas is equaling our integral. So that's a really, it's not that hard to read it. This is your vertical and this is your width. And then also if you let n, which is the number of rectangles, approach infinity, doing pretty much the same thing, it is equal to the integral of the function, which is the area under the curve. So the limit of any Riemann sum is always taken as the norm of the partitions. As the norm approaches 0, as the width of the partitions approach 0, the number of the rectangles will go to infinity, which will then give us that integration. So again, it's a little bit of notation. It's pretty in-depth there, but it's, again, really emphasizing what I'm trying to emphasize. We're jumping into this integral so quickly, and you don't want to forget the underlying foundation of why it works. And it's all based on Riemann's work, Riemann's sum. Okay, so now what? Now let's get in here. If I can find the right page of my notes. I have a mess. Patience. Okay, here it is. All right, now talking about that word integrable. Okay, integrable, I hope I've spelled this right. Integrable functions, meaning the function, can you integrate it? Okay, if you can't integrate it algebraically, then you just go to those lovely rectangles and make it happen. But there's a theorem on page 264 that we need to also look at when it comes to a function being integrable, or having integrability, as it says. Okay, and here's what it says on integrability. It says, and this is interesting, here's the word integrability. Integrability of continuous functions. If a function is continuous over an interval a to b, or if a function has finitely many jump discontinuities, then the definite integral will exist and f is integrable, which means we can integrate the function. The function does not have to be continuous for us to integrate it. In other words, it can jump, because when it jumps, we can still create like the rectangles underneath it of narrow width. So it can break and it can jump. So it's okay if it's a piecewise function, it is still integrable. So we can do that. So it can be if it's continuous, there's no issues whatsoever. But it's okay if it jumps so long as there are a limited number of jumps. It can't infinitely jump. You can't have infinitely many breaks in the function. It can't be a wild kind of function. But if it breaks a few times, it's okay. We can still integrate the function. We can still find the area under the curve. So this is something that kind of needed to know about. They talk about a function. It's really hard to find a function that is not integrable. But they do talk about a function over here where they define it as being rational or irrational. And this is a not integrable function. because this function jumps up and down erratically over 0 to 1, because it says, what does it say? The underlying fact is that between any two numbers there is both a rational number and an irrational number. So you have rational numbers and irrational numbers infinitely close to one another, more or less, and so this function is jumping around between 0 and 1 erratically, so it jumps, but it's jumping continuously, more or less, which makes it not integrable. So that would be a situation where you would not be able to integrate, and I'm not going to push that. You don't have to worry about that, but just a little more information that you know about. So now let's really finally get into this section. We're going to talk about properties of integrals. Okay, now that we have all the underlying concepts that we've just kind of brushed through, we have some properties of integrals. And one of them we're going to emphasize is if you integrate from a to b of f of x dx, which is finding the area under the curve between a and b, it is equal to the negative value if you reverse the limits. If you go from b to a instead of a to b on the same function, then when you integrate, it's going to be a negative value. So the change is when you change your interval from a to b and you reverse it from b to a, you're going to get a negative value. Now, why in the world is that true? Well, if you have a rectangle, or whose width is, say, a to b, when you compute, when you're finding the width, your width of this rectangle is b minus a, which is going to be a positive number because it's the large minus the small. But if you reverse it, because this reverses your upper and lower limits, if you reverse it and have to do a minus b, it's a negative value. So when you reverse the bounds, the upper and lower limits, when you reverse those, it causes your area to then be negative. So this is just one of our properties that you need to remember. You reverse my upper and lower limit, it's going to become negative. And when you do some homework, that will solidify, and you'll see that that's pretty easy. Okay, it's not that big a deal. Okay, here's another one. What if you integrate from a to a of a function? What do you think that equals? Equals 0. You're right. I mean, if you have no width, right, there is no width. You're sitting at a point. There's no difference between a and a. Then when you find area, which is length times width, and your width is 0, your area is going to be 0. So that's just very logical. This would periodically come up algebraically if you're working something algebraically or deriving something. You would have something crazy like that come up. But this is occurring because if your width is 0, then definitely your area under your curve is going to be 0. Now, those are two very basic ones that they put emphasis on because it's very logical. There are many that are very logical. And so if you look on your textbook, and I've made copies of this page, on page 266, this is what we're getting ready to discuss, are all these many rules of definite integrals. We just looked at number 1 and at number 2, and then we're going to look at these other ones, and we're going to make them logical. Okay, it's very easy if you take just a minute to look at the graphs. They do a beautiful job here with graphs at the bottom of this page to kind of emphasize or to get the concept to come across, or the physical vision of what the graphs look like, which make these properties hold true. Bless you. So I probably illegally copied this, but whatever. The one thing I don't like is that because it's in black and white, you're not getting the color on the graphs. But if you go into the electronic version of the book within Course Compass, you'll be able to see that color if you want to. So, but there they are. Most important is all that information in that lovely blue box right there. Okay, so let's take a look at it. We've already talked about if you change the order of your upper and lower bound, it's going to make the area negative. Talking about the 0 width, the area under a curve that has 0 width, of course, is 0. A constant multiple, k is a number like 5 or 6 or 3 or 10. It's just a number. So if you have 3 times your function, you can pull the 3 out front of the integration, only integrate the function, removing the constant from it. Well, they do a good job down here in your graph. This is part B where they're emphasizing the graph. If you're blue, the lower half is blue. If that's your function, and you multiply it times a number like a constant like 2, it's just going to raise it up or double it 2 is going to double the area under the curve. 3 would triple the area under the curve. So you don't have to integrate the 2. You just multiply the value of the area under the function times 2. And that's why you pull the constant out front of the integral symbol when you're algebraically coming up with the area under the curve. Okay? Then on number 4, they have the sum and the differences of 2 functions, or the area under the curve of 2 functions from a to b. And when you do that, you can split them up. Sometimes it's algebraically, it's easier to split them up. So you can integrate the first function and add it to the integral of the second, or subtract. Now, if you want a vision of what this looks like as area under the curve, again, they do a really good job of this on part C. If your f of x function is the lower blue part, and your g of x is the gray part, you add them together, the blue part just kind of lifts it up that same amount. So it's easy enough to say you add the blue to the, mine's kind of brown, you're going to get the green. So you can either add or subtract them because the area under the curve is just increased or decreased when you add 2 functions together, so long as they're both integrable. I'm going to enjoy that word for a little while. Okay, so that's the sum or difference. Additivity. God, these words. Okay. This one's pretty logical. Look at this. If you're integrating from a to b of f of x and then from b to c, okay, a to b and then from b to c, then it's just a to c of the function. Okay, so you go from the interval of a to b and then b to c, then you may as well just go all the way from a to c. So that's down here. Here is the graph. If you're going from a to b, which is the brown shaded region, and then from b to c, which is the blue shaded region, you may as well do the whole thing from a to c and get the same result. Okay, so you can combine it rather than breaking it apart. Just go all the way from a to c versus from a to b and then b to c. Then the max and min stuff. Woo, get back over here. If f has a minimum value, no. If f has a maximum value, max f, and a minimum value, min f, then, okay, your minimum of your function, minimum meaning the lowest point of your function, okay, you're talking about the height, a low vertical value of the function, times b minus a. Well, b minus a is the width. So you're looking at height times width. This is area. So you pick the lowest point on the function, give me the lowest vertical value, multiply it times the width of that rectangle, so it's the lowest part, lowest region, and this is the highest point of the graph times this width, the highest region of a rectangle, then all of the area would fall between the two. It'd fall between the two. And so they try to show, how did they do that? How did they do that? If your low point on F is the green area, and your high point on F is the brown line. So in other words, here's your low, okay, F of X is the blue line. Your low point here times the full width gives the green area. Your high right here of the function times all of this width would be the brown. So the brown area is underneath this whole rectangle. The green area is the lower half. Then they're saying the area under the blue is going to lie between the green area and the brown area. It really is very logical. Okay, we get in there and we're so algebraically integrating, we forget that this is a very simple, the concepts are very natural. And then domination, what's that one? Domination says if f of x is bigger than g of x, then the area under f of x is going to be greater than the area under g of x. That's totally logical, okay? Or if f of x is really high and large, then if f of x is greater than 0, then the integral of f of x, okay, if f of x is positive, then the area under the positive curve must also be positive and greater than or equal to 0. So those are logical. So I don't think you'll have any issues with that. So here's all of your properties, and this is a lot of what your homework is based on, is these properties. So this, like I said, it's going to be pretty straightforward, not difficult, but there's your copies of all those properties so that when you get into the homework, you might need to refer to that when you're hitting those questions. Okay. All right, so part D. Hang on to your handout, or you can always look it up in Course Compass, My Math Lab. Okay, so here's some examples. using those properties. All right. So, question number 1. Suppose you're given that the integral from 1 to 4 of f of x dx equals -2, and you're given that the integral from -1 to 1 of f of x dx equals 5, and you're given that the integral from -1 to 1 of h of x dx equals 7. So this is your given information. And notice that your area can be negative. If your shaded region is under the x-axis, your area is going to be negative because your vertical height is going to be a negative value. So your area can be negative if your shaded region is below the x-axis, which is why this can happen and get a negative value. So here's what your question is going to look like. Suppose they say, what is the value from 4 to 1 of f of x dx? Well, first of all, 4 to 1 is backwards. Okay, you go from 1 to 4, not 4 to 1. This is going backwards. So I would instantly rewrite this as 1 to 4 of a negative f of x dx. So when you reverse your upper and lower limits, you must make it negative. And then I look at my givens. It says that the integral of f of x dx from 1 to 4 is -2. So this is a negative of a -2. So that gives me an area under the curve of +2 between 1 and 4. Well, no, between the 4 and 1 was the original. Looking at it in reverse. Okay, here's another property. Suppose they ask me to integrate from -1 to 1 of 2 times f of x plus 3 times h of x dx. And when you're writing these integrals, kind of realize that the f of x, h of x stuff is your y value or your height, and d of x is your width. So this is like your height of your many numerous, infinitely many rectangles, and this is like your width that varies by Riemann sum. Okay, so to do this by all of these properties, I can split this up by going ahead and letting it be the integral from -1 to 1 of 2 f of x dx, and you've got to write that dx there, and the integral from -1 to 1 of 3 h of x dx. So I'm splitting it up. That property says I can split it up. Then I would pull the constant, the k, into the front of the integral. So this becomes 2, -1 to 1 of f of x dx, plus 3, -1 to 1 of h of x dx. This is by all those lovely properties give me this right. So now what was given to me? From -1 to 1, f of x dx is 5. So this is 2 times 5. -1 to 1 of h of x dx is 7. So this is 3 times 7. So this is 10 plus 21, which is an area of 31 square units. I told y'all this was not hard. Okay, let's try another one. You'll move through this homework quickly. Suppose you're integrating from -1. I'm going to be tight to get all this still on the screen. Suppose you're integrating from -1 to 4 of f of x dx. Well, you always look at your givens. Here's my f of x givens. Okay, these two at the top. -1 to 4. I don't have a -1 to 4. I have a +1 to 4 and a -1 to 1. So the way you handle this is you say, hey, well, -1 to 4 is the same as -1 to 1 plus 1 to 4. That kind of connects the two pieces. You take the first part and add it to the second part. And so long as this upper bound on the first one is the same as the lower bound on the second, then it's consecutive. You're not missing any space. Banking it right up against each other. So just visualize this. You go from -1 to 4 is what you're looking for. You're just breaking it up and going up from -1 to 1 and then 1 to 4. Yes, get me on the screen. So negative 1 to 4, you're changing it to add negative 1 to 1 and then 1 to 4. Okay, it was the whole thing. You split it into parts. This part plus this part. So in the given above and off the screen, from negative 1 to 1, this was 5. And from 1 to 4, it was a negative 2. So that area is 3 square units. So again, from negative 1 to 4, this is a very easy concept. From negative 1 to 4 is the same as taking negative 1 to 1 and adding it to 1 to 4. And I did that because of what they gave me. They gave me enough information to be able to do that. All right, let's try another one. This will be number 2. Given that the integral from 0 to 3 of f of x dx equals 3, it's a 3. And then the integral from 0 to 4 of f of x dx is 7, answer the following questions. Actually, there's only one. So here's the question. What is the integral from 3 to 4 of f of x dx? Okay, so you've got two pieces of information, 0, 1, 2, 3, 4. Okay, here's 0, here's 3, and here's 4. You've been given what 0 to 3 is, and you've been given what 0 to 4 is. So if you want to know 3 to 4, what do? There you go. Take the big minus the little. So this will be take the 0 to 4 value and subtract the 0 to 3 value. So it becomes 7 minus 3, which is an area of 4. Okay, so you can visualize that, hopefully, kind of got an image in your mind. Make that a little bit easier. Now, they haven't told me how to integrate, okay? They're giving me all these values for the areas and the curves on these intervals. They're going to show me some formulas for integration. They're not going to show me how to integrate. They're going to give me formulas for integration, and then they're going to only give me homework questions in this section that can be applied to the given formulas. So far, they're still saying these people don't know how to integrate. So you can't learn how to integrate. They're going to give you these formulas. So try to be patient. All right. So here is what they call known areas of integrals. Known areas of integrals. So they're going to ask me something like, or they're going to try to develop a little bit of a setup here as if you don't know how to integrate already, okay? And they say, suppose you're integrating from 0 to some number b of x dx. Okay, what is this? Okay, your function is x, which means your function is f of x equals x. That is your function. Well, if you graph f of x equaling x, starting at 0, if x is 0, if you draw a table here, if x is 0, y will be 0. If x is 1, y will be 1. If x is 2, y will be 2. So 1, 1, 2, 2, 3, 3, 4, 4. This is what your graph will look like. And your area is assumed always between this graph and the x-axis. So this is your region that you're trying to find the area for. Well, it's a triangle. So we know that the area of a triangle is 1/2 the base times the height. That's simple. It's 1/2 the base times the height. Well, the base is from 0 to b. So the width of the base of the triangle is b. What is the height? The height is also b, right? If this point is 1, 1, and this is 2, 2, and this is 3, 3, Then at B, it is BB. So the height is also a height of B. So your height is B. So we come up with 1/2 B squared by the division here, but really we're supposed to be in X. So when we integrate from 0 to B of X dx, then this actually equals 1/2. Well, they do leave it B squared because the upper interval is B. Okay, B squared. Now, we know that when you integrate X, it's 1/2 X squared, so that makes sense, but you got to put the B in there to get it when your upper limit is B. Now, this is assuming you're starting at 0. So there's your first little formula, but the formula gets a little better, and here are some what they call generalized formulas. And you will not use these very long, but you will be required to use these during this section. Generalized formulas. Now note this one doesn't say 0 to B, it says A to B, so you don't have to start at the origin. So if you're integrating from A to B of X dx, it equals B squared over 2, as we just found, minus A squared over 2 when your A is not 0. It works for A as being 0 too, but doesn't restrict your A to being 0, so long as A is less than B. Okay, another general formula they're going to give us is if you integrate from A to B of a constant like 10 dx or 7 dx, then this equals C times B minus A. Now, this one's very logical. If you have a graph, okay, if your function equals C, in other words, if your f of x equals C, like 10, then you'd be a horizontal line up here at C. Okay, it's a horizontal line. Like f of x equaling 10 is a horizontal line. So if you're going from A to B, then this is the region that you're finding the area under the curve. So if you look at area once again as being base times height or length times width, your width is the B minus A and your height is C. So your width is B minus A and your height is C. So that is strictly length times width. That's just a basic area of a rectangle formula for a constant graph. Okay. Suppose we integrate, they're only going to give us 3 formulas, from A to B of x squared dx. Then the formula for this, because you have an A and B are going to be numbers, is B cubed over 3 minus A cubed over 3, again, with the parameter that A is less than B. So those are the 3 formulas that you're going to use repeatedly to integrate. So you can only supposedly integrate now the function x, a number, or the function x squared. That's all you can do. That's all the power they're going to give you in section 5.3. We will outgrow this very quickly. Okay, when we start back in class on Monday, we're going to probably get a little further away from these limitations. But those are the 3 we're supposed to know and know well. Okay, so keep that handy. So here we go with some examples of using those formulas. Okay, examples using known area integrals. In other words, using those 3 formulas. Known area integrals. I'm going to put on here the 3 formulas. Known area integrals. So here we go. Number 1. Suppose they ask me to integrate from 4 to 7 of 2x plus 5 dx. And they have to put that in parentheses so that it doesn't look like 2x plus 5 dx. You know, it's 2x plus 5 dx. So we would go ahead and do this. There's my x. So we're going to rewrite this as the integral from 4 to 7 of 2x dx plus integral from 4 to 7 of 5 dx. Well, of the 3 formulas, all we know how to do is integrate x. This is my formulas. I know how to integrate x. So I got to get the 2 off. So I pull the 2 out from 4 to 7 of x dx plus integral from 4 to 7 of 5 dx. Okay, now we're ready. Okay, so this equals 2 times, by my formula, the integral of x dx is b squared over 2 minus a squared over 2. Well, your b, in this case, is 7, and your a is 4. Well, I'll go ahead and write this. The formula says b squared over 2 minus a squared over 2. Your b is going to be your 7, and your a is going to be your 4. And don't forget, and then you have the 4 to 7 of 5 dx. What is this one? This is a constant. When it was c dx, your answer was your width times your height. So this is 5 times my width. My width is 7 minus 4. My upper limit minus my lower limit, my b minus my a. So this is 2 times b squared is 7 squared, which is 49, over a squared, which is 4 squared, which is 16. Minus a squared, which is, well, that's a 2. That's a 2. It's a half. A squared is 16 over 2. This is 5 times 3. So this is 2 times 49 minus 16, which is 33, right? Plus 15. So this is 33 plus 15, which is 48. There it is. Okay. And that's how we work these problems, using those 3 formulas. All right, I'm going to post one. Whoa, come on, little train. Oh, dear. Thank you. Okay. Suppose we're going to integrate then from negative 2 to 4 of x halves plus 3 dx. We're going to break this down to an x somehow. So this is going to be an integral from negative 2 to 4 of x halves dx plus integral from negative 2 to 4 of 3 dx. Well, you got to get that half off of that x. So this is 1/2 integral from negative 2 to 4 of x dx plus the integral from negative 2 to 4 of 3 dx. Now by the formula we can do number 1, and by the formula we can do number 2 because that's a constant. So this is going to be 1/2 times b squared over 2 minus a squared over 2 by the formula. That's by the formula. And the second one by the formula is the height of 3 times the width, which is top minus bottom, which is 4 minus a negative 2. That's logical. If you're going from negative 2 to 4, this is 2 units plus 4 units. That's 6 width. So that you got to take top minus bottom. So this is 1/2 now. My b is 4. So 4 squared is 16 over 2. My a is a negative 2, and a negative 2 squared is a positive 4 over 2. And this is a plus a 3 times 6. So you can see this just becomes very easy. This is 16 plus 4, which is 20 halves, which is 10. So this is 5 plus 18, which is 23. Where is it plus? Because I messed up. I messed up royally. 21? That's a better number, isn't it? That's a number y'all like. What is the deal with 21? You can drink at 21. You can buy. Is that right? You have to be 21 to buy liquor. Is that right? I don't know those things. And you have to only be 16 to drive, right? And 18 to vote? Ooh, I'm smart. But you can drink while you're fighting in war. No, whatever. They really want. Can you, if you're in Europe, there's no age limit? In Europe, you have to be 18? Only 18.
People are like, you're a soldier? Forget the ID. What's 3 years?
We can't read your ID anyway. It's in English. Okay, here's a new formula, my X-squared formula. Where is that X-squared formula? Here it is. There it is. It's the b cubed over 3 minus a cubed over 3. So this one, strictly by the formula, and I've got to write the formula because I won't remember it. B cubed over 3 minus a cubed over 3. There it is. Okay, where the b is the cube root of 2, and the a is 1. So this integral is going to be the cube root of 2 cubed over 3 minus 1 cubed over 3. So this becomes 2/3 minus 1/3. This is some major rocket science work here. This is grueling. I told y'all it wasn't hard. I said y'all were going to have a good weekend. Okay, this one's a little bit of challenge, not a lot. Okay, -2 to 1 of the absolute value of x dx. Okay, what's the absolute value of business? Okay, you got to think about this. The definition of the absolute value is that if it's a positive number, it's just good old x. So if x is greater than or equal to 0, the absolute value of x equals x. But if x is a negative number like -3, you got to figure out how to make -3 to +3, right? So to make a negative number positive, you negate a negative number. So if x happens to be less than 0, meaning if x is negative, I have to make it positive. And to make a negative number positive, I negate it. So this is the definition of the absolute value of x. It's just good old x if x is positive, but if x is a negative number, you have to negate the negative number to force it to be positive. So here, x is going to be negative, so in this case, between -2 and 0, your x is a negative value. But between 0 and 1, your x is a positive value. So between -2 and 0, where the x is negative, you have to replace this with a negative x. But between 0 and 1, it's positive x. By the rules of absolute value, not by any switching the upper and lower limits or anything. This is just how the absolute value function works. So then this becomes negative out front of -2 to 0 x dx. And this one's fine. So, cool, the formula was b squared, right, over a. Yeah, 2. Negative out front of b squared over 2 minus a squared over 2. And this one, again, is going to be b squared over 2 minus a squared over 2. This is the b is 0 in this case, and the a is -2. So on the first one, b is 0, and a is -2. And the second one, b is 1, and a is 0. So you still got this negative out here. You have 0 minus 2, right? This is 0 minus 4/2, so 0 minus 2. So this is a -2, and this is just a half. So you have 2 plus a half, which is 3/2. No, 2 plus half is 2.5, which is 5/2. So watch, just be careful. Okay, that's not a difficult question. Just be careful. Okay. Now they do something a little tricky, and this always seems to be on a test, and y'all seem to have difficulty with it on a test because it throws away all algebra, and it just is basic geometry. And so you have to remember, oh, I'm not going to be able to do this algebraically. I'm going to have to just use geometry. So you have to convert your mindset when you do these. So you have to really look at what's given and recognize it for what it is. And it's going to be what we call half circles or semicircles. So I'm going to say integration of half circles. Try to kind of remember this. You've got to really recognize the equation to remember to use geometry. Okay, you're not really using any true methods of calculus. You're only using geometry. Okay, we know that the area of a circle is pi r squared. So if we have a semicircle or a semicircle, however you want to talk about it, which is the top half or half the circle, then the area is 1/2 pi r squared, like a sunburst. Now, you need to remember, this is what's going to have to trigger you to do this rather than using any forms of calculus. The formula or the equation for a circle is something like x squared plus y squared equaling r squared. That's your formula or your equation for a circle. So if your equation says x squared plus y squared equals 36, this is a circle whose radius is 6. Now, if I solve this equation for y, it's going to say y equaling plus minus the square root of 36 minus x squared. So anytime you see a radical that has a perfect square in it like that, think, I bet this is a circle. Now, if you want to graph this on the calculator in order to get the whole circle, remember what you have to do. You have to graph the positive version and the negative version to get the whole circle, right? The positive version gives you the top half of the circle. The negative version gives you the bottom half of the circle. So you have to graph it in two pieces in order to get a full circle in your graph. And I hope y'all remember this. I guess we did this, I don't know when we did this, maybe in college algebra or something. So if you're on your calculator, this will really lock this down. If you, okay, Miss Coleman, what you been doing on this calculator? Okay, if you put in here just the square root of something, whoops, back up. Of some, go back, okay. Something like 36 minus x squared, and you graph it, and I'm going to do a zoom standard because I don't know what's been going on this calculator. Oh. Okay. It's going to only give you the top half of the circle because you're only looking at the positive radical. If you want the whole circle, you have to put also the negative. How did I get that in y too? Oh, well. You have to put the negative version in there. Ah, that didn't work, did it? Almost. Oh, I double-clicked. But it still worked. There you go. There's your negative version. Now when you graph, it'll have the top half and the bottom half and give you the whole circle. The reason it looks like an ellipse is because this is a rectangular screen instead of a perfectly square screen. So our horizontal axis is always bigger than our vertical axis on this calculator, so it skews it. But you have to have the top and the bottom. Well, when you look in the book or in my Math Lab course compass, they're not going to give you the plus minus in front of the radical. They're only going to give you the plus. So they're only going to ask you for the area of the top half of the circle. So you're pretty much always going to be looking at the 1/2 version. So when they don't put a plus minus in front of the radical, you only assume the positive and you only assume the top half. And you can assume that. You have that right, and that's what they expect you to do. So if they ask you a question like, integrate from -2 to 2 of the square root of 4 minus x squared dx, you don't think, well, I wonder if I have a formula for this. That doesn't come across your mind at all. You look at this and say, hey, man, this is a circle with a radius of 2. And it's going from -2 to 2, which is perfectly logical since this is a circle of radius 2. So it's going from -2 to 2 with the radius of 2. This is definitely a semicircle. So I don't do any calculus. I just say the area of this thing is 1/2 pi r squared. My r is 2. So this is 4/2 pi. The area of this thing is 2 pi. Has no reference to any formulas or any methods of integration. It is simply a very basic concept. So the minute you see something like this in a radical, you got to think, no calculus today. This is sheer geometry. Okay, so what's going to be the answer of this one? Suppose it says -4 to 0 of the square root of 16 minus x squared dx. He says 8 pi. Anybody agree or disagree with 8 pi? We have an agreeable person. Does anybody want to not agree with 8 pi? Okay, little geometry students out there. Ooh, we got a 4 pi. It's like an auction up here. Okay, this is a radius of 4, right? 1, 2, 3, 4. 1, 2, 3, 4. There's your half circle, right? Are we going from -4 to 4? Or are we going from -4? Are we going from -4 to 4? We're going from -4 to 0, right? You see it? We're only doing this part. This doesn't say -4 to 4. It says -4 to 0. So this one is 1/4 of pi r squared. So this is 1/4 of pi times 4 squared, which is 4 pi. So watch your bounds, watch your upper and lower limits. That's a lousy circle, half circle. Circles are not easy to draw. Y'all say just as bad. Sometimes. Like how many thank goodness we have lots of letters in our alphabet. H. Average value of a function. We've already done a little bit of this. Remember, the average value of a function is not the average area under the function or the average width. It is the average height of the function. The average y value. Okay? Just keep that in your head. So, we already said that if we have the area of a rectangle being length times width, where we consider length height times width, then the height will be the area divided by the width. Well, if we want the average height, then the average height is going to be the total area, which we usually compute with integration, divided by the total width. Okay, so on the top, we're going to integrate something, because that's going to give me the total area under the curve. And on the bottom, we're going to do b minus a, which is the width of the interval from a to b. So that's what you're going to do. So when they say so here's what the formula is. Here's how they write it. The average f, that's how they write it. The average f, AVG of f, is going to be 1 over b minus a. This is the division, 1 over width. This is 1 over width. And this is 1 over your total width times your area, which is to integrate your f of x dx from a to b. Okay, that's logical. You don't have to memorize that. Make it logical. So then if they ask you a question, what is the average value of f of x? And then they say f of x equals 3x squared minus 2 on the interval from 0 to 1. That means what is pretty much the average height of that function between 0 and 1? How high does it go? It's that water sloshing around that tanker truck with that person trying to move the flag from one end to the other while they're flying down the road at 50 miles an hour or something crazy. And they're turning the truck. He has to do like a pattern around cones or something. Okay, so we've been given the whole little formula up there, which is 1 over b minus a integration of a to b f of x dx. Okay, so this is 1 over b minus a is 1 minus 0, it's a width of 1, from 0 to 1 of 3x squared minus 2 dx. Okay, now you go back to your three formulas and see which one applies, which ones apply. So this is 1 times the integral from 0 to 1 of 3x squared minus 2 dx, because your width is 1 over 1. So now we break this up, and this is going to be 3 times 0 to 1 of x squared dx minus the integral of 2 dx from 0 to 1 by all of those properties of integration. So this is 3 times, this was the b cubed over 3 formula, right? B cubed over 3 minus a cubed over 3. We will learn how to do this algebraically in the near future. Yeah. Okay, so this was the b cubed over 3 minus the a cubed over 3 minus, this is going to be 2, which is your height, times your width, which is 1 minus 0. So this is going to be 3. Your b is 1 cubed over 3. And your a, this is your b and your a on the first integral, is 0 cubed over 3, top minus bottom. So this is 3 times 1/3, which is 1, minus 2, which is an area of negative 1. And how can your area be a negative value? No, not your area. I'm sorry. This is not area. What is this? This is average value. This means the average height of this function is 1 unit below the x-axis. Mm-hmm.
So the squared doesn't matter or anything?
Where's the squared?
Like it says 3x squared, because on the formula it's just x.
You have 1 for x squared.
Right. We have the third formula was x squared formula. Remember there were 3 formulas, your x, your constant, and your x squared. Here they are. Your x one, your c one, and your x squared one. There's 3 formulas. Every time you look up, I move this piece of paper just in time for you to not see it. Okay. Anyway, so if you look at this graph, and I graphed it very quickly, but where are we going? We're going from 0 to 1. If you go from 0 to 1 on this graph, it crosses, when y is 0, it's like 2/3 or something. So it's way down here. At 0, it's at negative 2. Way down here. So the graph looks like this, something like this. And so if you look at it, you have your average height of this function is down here. If you took your high y's and your low y's, you got a lot of negative y's, a lot of low y's, a lot of positive y's, your average is going to fall down here somewhere. Your average height of your function is down here around negative 1. So it's logical. Makes sense. Okay, so guys, we are through. You have 3 formulas. When you have a circle, you don't use a formula, okay? You just geometrically do pi r squared or half of it or a fourth of it, whatever falls in that you have to do. Y'all have a great weekend. Your homework, again, is not going to be difficult. And enjoy this gorgeous weather.